Welcome to tonight's video on section 3.2, logarithmic functions. Remember, the purpose of a logarithmic function is that it is the inverse of the exponential function. So if you notice, the exponential function is here, the b to the x, and to find the inverse, first remember we replace f of x with y, and then you switch the x's and y's. So you get to this point, x equals b to the y. And now you're supposed to solve for y, but the problem is there's no way algebraically to get that y out of the exponent. So in order to isolate the y, logarithmic notation was created so that you could have the inverse function of an exponential. So the logarithmic function y equals log base b of x is equivalent to b to the y equals x. Notice that x has to be greater than 0, and the base has to be greater than 0, but not equal to 1. So notice if you compare the two forms, the y is equal to the exponent, the b is equal to the base, and the x is equal to the answer. So changing from logarithmic to exponential form. So here, notice the base is 5, the exponent is 2, and the answer is x. Here the base is 3, the exponent is y, the answer is 7. To go the other way, the base is 12, so you're going to say log base 12, the answer is x of x equals the exponent 2. So when you say it, you say log base 12 of x is 2. That's the proper way to say it. So here it's log base b of 8 is equal to 3. Some of these logarithms can be simplified rather easily. For example, log base 2 of 16. So 2 to what power is 16? And the answer is 4. Log base 7 of 1 over 49. Well, 7 to what power is equal to 1 over 49? The answer is negative 2. Basic logarithmic properties. The first one is if the base and the answer are the same, it has to equal 1. Because think of it this way, log base 5 of 5, that would equal 1, because 5 to the first is 5. Also, if you have log of any base of 1, it's always equal to 0, since b to the 0, anything to the 0 power is 1. So log base 3 of 1, that would equal 0. So here are some examples. Log base 7 of 7, that's equal to 1. And log base 5 of 1, that's equal to 0. There are also inverse properties. The inverse properties come from the fact that the two functions are inverses. F of x equals b to the x. And the inverse is the log base b of x. Remember, when you do the compositions of inverses, that they should equal x. So if I do the composition here, f of log base b of x should equal x. So I take this log base b and I put it into the x here. So I get b to the log base b of x power equals x. So what that means is if you have a number and it's raised to the log of the same base, then the answer is just whatever that answer is. So here 6 to the log base 6 of 9 power is just equal to 9. On the other hand, if I did f inverse of f of x, that should equal x as well. So if I do f inverse of b to the x, that should equal x. So basically what it's saying is log base b of b to the x is equal to x. So for example, if you look here, log base 4 of 4 to the 5th, that should equal 5. And those properties are true because they are inverses of each other. Graphing logarithms, what you have to remember is that this is saying basically 3 to the y equals x. So if I were to make a table, it would probably be in my best interest to put numbers in for y. So if y is equal to -1, x is equal to 1/3, because 3 to the negative first is 1/3. If y is equal to 0, 3 to the 0 is equal to 1. If y is equal to 1, then 3 to the first is equal to 3. You also have to consider that you can't raise a number to a power and get zeros or a negative. So there's going to be a vertical asymptote at x equals 0. So when you graph this, you have 3, 1, 1, 0, and -1 and 1/3. Sorry, 1/3 and -1. So it looks like that. That's log base 3 of x. If you compare that to the exponential function y equals 3 to the x, remember where the base points were -1 and 1/3, 0 and 1, and 1 and 3. And notice it had a horizontal asymptote at y equals 0. So it looked like this. Like that. So notice that's 3 to the x. So notice how they're inverses because the x's and y's switch as well. So characteristics of logarithmic function, notice the domain is always greater than 0. The range now is all real numbers. That's switched from the exponential function. If the base is greater than 1, it rises from left to right. Notice this rises from left to right. And if the base is between 0 and 1, it would fall from left to right. The vertical asymptote is x equals 0. And notice the base points, 1 over b and -1, 1, 0, b, 1. Those are just the reverse of the exponential function. And the vertical asymptote's at x equals 0. So now when we graph this, the first thing we're going to be asked to do is put this in standard form. Standard form meaning we're going to take out the number in front of the x. Sorry about that. We're going to take out the number in front of the x. So it's log base 4 of 16 times -x plus 2 plus 3. Because one of the things we know is that log base 4 of 16 is actually equal to 2. So we're going to take that 2 and multiply it. So now it's log base 4 of -x plus 2 plus 3. And now the only thing left to do is within this parenthesis is to factor the negative, because that helps us with the horizontal shift. So this is the standard form of it. Remember, we can't take the -16 out because 4 to a power will never equal -16. So we're going to have to leave the negative inside. So this is the one function where we will have a reflection across the y-axis. So the standard base function here, well, the base is 4, so it's log base 4 of x. The transformations, well, remember we start horizontal, so we start inside, and since there's a negative, that means there's a reflection across the y-axis, which means that's -x. Then, because it's -2, we're going horizontally to the right 2, horizontal shift, right 2, so that's x plus 2. Then there's a vertical stretch by 2, so it's 2y. And then the last thing is there's a vertical shift up 3. So there are the 4 transformations. There's actually 5 total. Notice we didn't have, A wasn't negative, so there wasn't a reflection across the x-axis. So now we'll make our table. Let me make this a little bigger. So next we have to make our table with the original points and the transformations. So remember, the original points are 1 over b, negative 1, 1, 0, 1, b, so the base is 4, and then you have vertical asymptote at x equals 0. So you have a negative x, you have x plus 2, you have 2y, and y plus 3. So when you do your transformations, negative 1/4, negative 1/4 plus 2, that's 7/4. And then 2 times negative 1 is negative 2, plus 3 is 1. And then negative x here is negative 1. And then plus 2 is positive 1. And then times 2 for y is still 0, but then plus 3. Sorry, I wrote this backwards. It should be 4, 1 and not 1, 4. Because it's the base and 1. So it's negative 4. And then plus 2 is negative 2. And then 2 times y is 2. And then plus 3 is 5. The vertical asymptote at x equals 0, well, negative times 0 is still 0. But then plus 2 makes it at 2. And then the y's don't affect the vertical asymptote. So there are points. We don't have to worry about the x and y intercepts. So we're going to sketch the graph. X equals 2 is our vertical asymptote. And then we have 7/4 and 1, which is like right there. Then we have 1 and 3. And then we have negative 2 and 5. And so our graph goes like that. Our domain is all the numbers less than 2, and our range is all real numbers. All right, so if you weren't given a graph, but you wanted to find the domain of a logarithmic function, you just set the answer greater than 0. So x minus 5 would have to be greater than 0. So x is greater than 5. So your domain here would be from 5 to infinity. That's if you weren't given the graph, how you would find the domain. Anytime you have a log and there's no number as the base, it's assumed that it's base 10. So whenever you use your calculator, it's always log base 10. So if I say log 100, I'm asking 10 to what power equals 100? So that's equal to 2. All right, so anytime you just see log, it's assumed that that base is 10. That's the common logarithm. There's also the natural logarithm, which means the base is e. And instead of writing log base e, they write ln. But you can assume that there's an e as the base. So if I say ln of 4, that means e to what power is equal to 4. That's what that means. Finding the domain is the same as any other logarithmic function. I would take 4 minus x and make it greater than 0. And then I'd subtract. And then divide by the negative means you flip the sign so that you get x is less than 4. So it's from negative infinity to 4. All right, I hope this video has helped, and I will see you guys in class. Have a good evening.